Okay, so we just gave the 2 minutes that we promised. So welcome everyone to the IPARCOS astro-seminars of the Universidad Complutense de Madrid. And well, we will first, of course, would like to thank Nuria Álvarez Crespo, which is our speaker today. Thank you, Nuria, for teaching us a little bit more about the massive galaxies and submillimetre galaxies in particular. And well, Nuria is actually a former graduate for the Complutense University. She also did the master at the Complutense University. And she actually did the PhD at the Turin University in Italy on large-scale environments of low luminosity radio-low AGNs. And also she spent some months during that PhD at the CFA Center for Astrophysics in the Harvard University in Cambridge. And then she had a postdoc a short postdoc at the University of Zagreb in Croatia. And since almost 3 years ago, she's now at the ESA, at the European Space Agency Space Science Center at the Villafranca del Castillo near Madrid. And so again, thank you very much, Nuria. It's especially, let's say, happy for us since you already, I know you from the time you were a master's student, so it's particularly exciting for me to hear everything you have done in the last few years and also recently. So please, thanks again on behalf of also Santi and Patricia, which are the organizers of the symposia and the meetings. And well, thanks again. And thanks everyone for connecting and joining. Thanks.
Thank you for inviting me. It was not so long ago when I was listening to this. Not so long.
Not so long.
When I was listening to this very same seminar. So I'm very happy that I'm able to do one today. So I'm going to start sharing my screen. Well, if I hit the button share screen, it's better. Okay. Can you see my screen?
Yeah, perfect.
Okay. So today I'm going to talk about the environments. You can see these, right? I should. Okay. About the environments of submillimetre galaxies in the cosmos field. And this is a work that has been done in collaboration with Bernesa Smolcic, Alexis Finowenov, Laia Barrufet, and Manuel Aravena in the frame of the Cosmos collaboration. And this talk kind of overlaps with last week's talk that Carlos Gómez Guijarro made. And he talked more about the evolution of these galaxies also in the cosmos field. But today I'm going to talk about the environments in which these galaxies live and form and evolve. So if you haven't watched his talk already, I invite you to do it in the YouTube channel, but not now. Just wait until the end. So I don't know how can I keep moving. Okay, so this is a small outline of what I'm going to talk today. First, I'm going to make an introduction in submillimetre galaxies. Then I will talk a little bit about clusters and protoclusters of galaxies. And then I will speak about the work that we've been done in the galactic environments of submillimetre galaxies. I will explain what is the Cosmos Survey, why we chose to do this kind of analysis with the Cosmos Survey. I'll explain the submillimetre galaxy sample that we're using and its properties. Then the Cosmos catalogs and the properties and things that need to be addressed to understand this kind of analysis. And then I will explain the method using first the photometric overdensities. Then we test these methods using spectroscopy. We also search for X-rays around these sources because that is that indicates if there's the intergalactic medium of the cluster. I will explain a little bit the meaning of these overdensities in some multi-components of submillimetre galaxies, and of course finish with some summary conclusions and future work. So for years, the window to the submillimetre universe was obscure due to many technical difficulties because it was a challenge to build sensitive detectors at these wavelengths. So only in the 90s, the advances of submillimetre detector technologies opened this window to the distant universe. So the first surveys, they were done using the SCUBA camera at the James Clerk Maxwell Telescope in Hawaii and the MAMBO camera at the IRAM telescope in Sierra Nevada, in Spain, and these surveys, they revealed a population that of obscure galaxies highly embedded in dust that they were not detected so far in deep optical surveys. They were very luminous, they were at high redshift, and these are the submillimeter galaxies. These galaxies are extremely luminous, and they emit most of their energy in the submillimeter. And many times they are faint in other wavelengths, so follow-up observations are very challenging. So as you can see in this image, so the image is done in optical with a combination of several telescopes, and you can see that the overlaid is the white contours, that is the submillimeter emission. So you can see that it's not straightforward to say which one is the counterpart of these galaxies. Here you can even see that you don't see anything in the optical. So it's a bit challenging to understand this. And these galaxies, they are going through an episode of extreme star formation with star formation rates of thousands of solar masses per year. And this indicates that they are very rich in gas, and probably they are driven by mergers, that they are very rich in gas and they are triggering this extreme star formation. They are found at redshift higher than 2. This means they live very early on in the universe during its first 3 gigayears years, and many of them can even be found at redshift higher than 5, which means the beginning of the universe, so only 9% the age of the universe today. And at these distances, they generate a significant fraction of the energy output of all galaxies in the early universe. The reason why they are so strong emitters in the submillimeter is because they are highly obscured. So they have a lot of dust. These galaxies are embedded in dust. So these grains of this interstellar gas are heated to temperatures between 20 and 200 Kelvin by a population of young massive stars. Then this dust re-emits this emission from the stars in the form of thermal emission, emitting this modified black body spectrum. Most of the emission, like 99% of the emission, is this dust emission, but there's a little fraction that comes from molecular rotation and atomic fine structure transition lines. So here I'm going to talk a little bit about the evolution of these galaxies, but this is a hot topic in astrophysics today. And actually all the talk from Carlos Gomez Guijarro from last week was about the evolution of these galaxies. So, and also there was an interesting discussion after his talk. So I don't want to get into detail. I just want to give a small glimpse into this evolutionary path, like a general picture. So it is thought that in the early universe, they were merger-rich mergers, that they were very rich in gas, that trigger a lot of star formation in the galaxies, creating these dusty nuclear starbars or submillimeter galaxies. Then it is thought that there is some process that quenches or stops this star formation. It can be a quasar. So the galaxy, the star formation stops, and they become in the compact quiescent galaxies that we see in the universe at redshift 2, more or less. Then they grow in size, but not in star forming. So they grow through dry mergers, becoming the giant local elliptical galaxies that we see in the universe today. And now I move on to clusters. So clusters are the largest gravitationally bound systems in the universe. So you see this sentence in every paper, every presentation, everything you see about galaxy clusters. So you can take a shot of whatever you want every time you hear this sentence, but just because it's true. So they are aggregates of 50 to thousands of galaxies. This number is not fixed. I mean, it doesn't mean that if there is 49 galaxies that it's not a cluster. It's just an approximation. They are gravitationally bound, big systems of galaxies that they are gravitationally bound. And most of the galaxies that belong to galaxy clusters, they are quiescent galaxies. So they are elliptical, they are very red, they are not forming stars. Most of the matter that exists in galaxy clusters is dark matter, and then the next in line is the intergalactic medium. This intergalactic medium is a hot plasma that lies between galaxies, and it gets heated. It gets heated to temperatures so high that it emits in the X-rays. So it is possible to search for a galaxy cluster looking at the X-ray emission, extended emission of the intergalactic medium. Another typical way of searching for galaxy clusters is very straightforward, is counting the number of galaxies in a region of the sky, and if the density is very high, then you have a galaxy cluster. The progenitors of the clusters that we see in the local universe, they are protoclusters. So they are early overdensities of dark matter and massive galaxies that they merge hierarchically to form a cluster in our local universe. So protoclusters are very big structures. They extend about tens of megaparsecs, split into a number of dark matter halos in unbounded regions. They are at redshift higher than 2. So as So as you can see here, this is taken from this is is an schematic representation. This is at redshift 4, this is at 2, and this is at 0. So you can see this is very big. And then when it comes to the earlier on in time, then it becomes virialized and becoming the clusters that we see in the local universe. They are very difficult to observe, and contrary to galaxies or to clusters in the local universe, they are formed of star-forming galaxies. So the relationship between the properties of the galaxies and the location in protoclusters is important to understand the cluster formation and evolution. So in galaxy protoclusters, star-forming galaxies are expected to illuminate the high-density dark matter nodes of a protocluster region. So an efficient way to search for protoclusters is to look for concentrations of bright star-forming galaxies. So this can be done in the ultraviolet or in the optical, but we are missing the dust obscured star formation. So we are missing the submillimetre galaxies. So this is where our submillimetre galaxies come at play. So if we find that if submillimetre galaxies are found predominantly at high redshift galactic environments, they can be used as tracers of protoclusters. So that can make people's life easier. Also, if submillimetre galaxies are indeed the progenitors of massive elliptical galaxies are found in galaxy clusters, so they should be also found in high density regions. So basically we need to study these galaxies to put them in a cosmological context. So also studying their environments can give us hints about how they form, because different models give us different clustering ideas. So if submillimetre galaxies are thought as a long-lived episode of star formation, these kind of models, they give that these galaxies are strongly clustered, while for other models, submillimetre galaxies are short bursts. That leads to a weaker clustering. So studying the clustering can make us distinguish between these kind of models. Also, if submillimetre galaxies are found in similar regions as quasars, that would mean that quasars are the event that quenches the star formation. So that path, that evolutionary path that we think that submillimetre galaxies follow, that may be correct. So to perform this kind of study, we need the data that is both extended enough to be able to trace these large structures, and it's also deep because these galaxies are at high redshift. So this is given by Cosmos. Cosmos is the optical tool for this goal. So Cosmos is an astronomical survey that is specifically designed to measure properties of individual galaxies and the structure in the universe at the same time. So this allows us to understand how the largest systems influence the smaller ones and how this interplay changes with time. So the survey covers 2 square degrees in the sky, a patch that is roughly 16 times the size of the moon, in the constellation Sextant, which is a field that is near the equator. So this part of the sky was chosen because it is visible for both telescopes in the northern and in the southern hemisphere. And in that particular region, there are few stars and few clouds of gas that block our view into the deep parts of the universe. So over 2 million galaxies have been observed, spanning 75% the age of the universe. And these 2 square degrees are covered with both photometry and spectroscopy, and from the X-rays to the radio wavelengths by a lot of telescopes. So this gives us, this is the instruments that have observed these patches of the sky. So you can see there is ultraviolet, optical, infrared, X-rays, radio, optical, near infrared, radio again. So this gives us a panchromatic view in the sky, so we can be able to not obtain a skewed view of the universe, but a multi-wavelength, the multi-wavelength properties. So this is the end of the introduction. So now I begin to talk about the work that we've been done. So up to now, like the many previous submillimeter galaxy studies, they were based either on small samples or samples that were not so well defined. So the conclusions that we were able to extract from them, they were not so general. So here we studied for the first time hundreds of submillimeter galaxies from a well-defined population. It was first discovered by the camera Aztec in the Aztec telescope in the Atacama Desert in the northern Chile, and then they were made a follow-up by ALMA in 96 fields of the sky. This means that these 116 submillimeter galaxies are in these 96 fields. So several of these fields have several galaxies, but I will get into that later. All of these submillimeter galaxies belong to the cosmos region or to the cosmos field. So we are able to study them using, taking advantage of this survey. So they observed 152 galaxies, but we take what they call the strict sample. So those submillimeter galaxies for which there is a spectroscopic or an ambiguous photometric redshift. So here you can see, this is the redshift distribution in red. The other is the full sample, so forget about it, just focus on the red part. So this is the redshift distribution of our submillimeter galaxies. 30 of them have a spectroscopic redshift, and the median redshift of our sources is 2.3, but you can see there is a tail that goes up to 5. Here is the distribution of sources at fluxes lower than 1.2, I think 1.2.5, higher than 1.8, and in between. So the tendency that you can see is that brighter sources are found at a higher redshift. So to study the environments of these sources, as I said again, we need data that is both is uniform, it's extended enough, and it's deep enough. And this is given by the Cosmos Photometric Catalog. The Cosmos Photometric Catalog gives photometric redshift and stellar masses for more than 500,000 objects over the 2 square degrees of the cosmos field. And the coverage is fairly uniform. That is very important for our conclusions, to extract conclusions. We also use a spectroscopic catalog. This spectroscopic catalog is not public, so it's only available for members of the Cosmos collaboration internally. And it's a compilation of all available spectroscopic redshifts for this region of the sky. So it's a compilation of different catalogs. And this time, for this spectroscopic catalog, the coverage is not uniform. So this is going to be important in the next. So first of all, what we need to address is to know if the photometric redshift accuracy is good enough for us to be using it to study the overdensities of these galaxies. So we divide the Cosmos catalog, the photometric catalog, into two redshift bins, one at redshift lower than 3.5 and one at redshift higher than 3.5. So 15,000 of the sources at redshift lower than 3.5, they also have secure spectroscopic redshift. So we can make a comparison between the spectroscopic and the photometric redshift. We make a distribution, and we see that the deviation of the distribution is very, very low. The standard deviation of the distribution is 0.067. So this gives us a good photometric redshift accuracy at redshift lower than 3.5. We do the same at redshift higher than 3.5. This time there are many less objects, but with the 200 sources that we have, we obtain a fairly good photometric redshift accuracy. So we conclude that there is good photometric redshift accuracy. So we move on to use this catalog to study the overdensities. So how do we study the overdensities? So conceptually, this is easy, but it's not so easy to explain in a talk, particularly online. So I will try to do my best. So for each submillimeter galaxy at a certain redshift, we take one redshift bin. I mean, we take the sources from the Cosmos photometric catalog that add at the same redshift bin of the redshift of the submillimeter galaxy. Is given by the distribution, I mean, it's given by the redshift of the submillimeter galaxy and a distribution that we said before. And we take several radius, 0.5, 1, I mean, this is a sample for one source. So this is the submillimeter galaxy, and this is the galaxies in a radius of 5. And we measure in each one of these radius the overdensity parameter. Basically, if the overdensity parameter is higher than a threshold, then the submillimeter galaxy is in an overdensity. If it's below that threshold, is in an underdensity, so it's in a void of the sky. And if it's similar to that redshift, then it is indistinguishable from field galaxies. What is this overdensity parameter? Well, the top part is defined by the local galaxy density. Is just the number of galaxies at that redshift in that radius divided by the area of that radius. And the other parameter is defined by the background. So all the galaxies in the Cosmos catalog that are in that redshift bin in the entire area of the Cosmos field. And how do we define that threshold? So we define the false detection probability. So for each submillimeter galaxy at a certain redshift, we make 10 mock catalogs. So we place 10 times in a random region of the sky this submillimeter galaxy. Then for each one of these 10 mock catalogs, we make 1,000 more catalogs, taking all the galaxies from the Cosmos field, all of them, in that redshift bin, and we place them randomly in the sky. And we measure the overdensity parameter. So at the end, we have 10,000 catalogs for each submillimeter galaxy. So the threshold is the probability that a number of sources that are found for that same submillimeter galaxies are found within a radius is lower than 5%. I don't know if I explain myself well or not. Okay, so what we get at the end, this is the overdensity parameter versus the radio. So here you can see for each one of the radius, the value of the overdensity parameter. Next to each radius is the number of galaxies that are found within that radius. And if that galaxy is found in an overdensity, then the point is enclosed in a square. So what we find is that 27% of our submillimeter galaxies are located in a high density environment. And in those cases where they, this is the sample that is found in a galactic dense environment. And you see that every time we find them in a galactic dense environment, the radius at which we find this overdensity is the first one we're measuring. So only 3.5 arc minutes. So only for 6 of these sources, the radius at which we find the overdensity is higher than 0.5. This means our overdensities are very compact. And at all redshift, we find that more of that all the time, they are measured at 200 per kiloparsec. That is the size of the overdensity. So this is in agreement with previous studies about submillimeter galaxies. They find more or less the same. They always find a 30% of the submillimeter galaxies in a clustered environment. They also find the same size of the overdensity, and also this is in agreement with previous studies about quasars. So they at high redshift. So this supports the idea that quasars are those mechanisms that quench the star formation. Also, we do not find the clustering strength evolution with redshift. Here you can find the distribution in yellow. There is the redshift distribution of those sources that were not found in an overdensity, and in gray, those sources that were found in an overdensity. And there is no difference between the distribution of these sources. And this is still a matter of debate in the literature, because some of them do not find an evolution with redshift, while other studies do find that submillimeter galaxies are strongly clustered at higher redshift. But there are too many biases involved to see if this is actually physical or it's just a bias that we are not able to address the clustering of the sources at high redshift. So to start, there is, our galaxy sample is limited in flux, so we might be missing those sources that are fainter. So we might be missing overdensities due to that effect. Also, there is a 20% of incompleteness in the Cosmos catalog for a method, because the method by that they're measuring the photometric redshift, it fails 20% of the times. And also there is catastrophic failures in photometric redshift of 13%, also a redshift higher than 3. If that is not enough, using photometric redshift is known that it dilutes the signal of the overdensity parameter. So we might be missing those environments that are not so dense. So again, we don't know if this is physical or this is just a bias. We have 30 sources for which there is a spectroscopic redshift, and 15 of them are found in an overdensity. So we try to test if that overdensity is true or not using the spectroscopic catalog. So 7 of them are found in an overdensity, so they are confirmed. The problem with the spectroscopy is that the Cosmos catalog, the spectroscopic catalog, the coverage is not uniform. So you cannot, since it is not uniform, you cannot use it to make the study. So you cannot use it like the photometric redshift to make the study. You can only use it to test if actually what you found using photometry is true. Also, there is only 300 sources that are at redshift higher than 3.5, so that is very low. That's why these effects limit the conclusions that we can extract from this analysis, and this can only be used as a confirmation. Additionally, since groups and clusters of galaxies, they emit in the X-rays, and the cosmos field have been mapped many times with XMM and Chandra, we take a catalog that is made by Gonzalez et al. In 2019, And they made a catalog of 247 X-ray groups, clusters. I mean, the mass is kind of in between these two populations. And 11 of our sources fall at the same redshift of these galaxy clusters. So we make a cross match between the position of our submillimeter galaxies and other galaxy clusters, but we didn't find any match. We didn't find any results. But this could be due to the fact that, again, the pointing is not uniform. So only the central part, the central degree, the 1 degree of the central part of the Cosmos survey has been covered more times. So this might also bias our results. Also, as I said again, we have 160 different submillimeter galaxies, but they are observed in 96 different ALMA fields. So 20 observations contain more than 1 submillimeter galaxy, but 11 counterparts are not in the strict sample. That's why here you can see only that I'm analyzing 9 fields. So the fact that they are together in the same field is because either they are gravitationally bounded, so they are physically related, or it's just a chance alignment because they are the projection is close in the sky. So combining the redshift, combining the projected distance, and the membership to an overdensity, we try to address which one of these sources is physically related and which are not. So 3 of these systems, we found that they are gravitationally bounded, so all of them belong to an overdensity. The redshift is already close and the projected distance is close, so they are together. For 4 of them, the fact that they are seen together is only because due to chance alignment, because the redshift is too far apart. And for 2 systems, it is dubious because the redshift is, they are close to one another, and the projected distance, they are close to one another, but one of them are found to belong to an overdensity, and the other is not found to belong to an overdensity. But this could be due to the fact that in our method, we are considering that the submillimeter galaxy is at the center of the overdensity. So it can happen that one of them is at the center of the overdensity and one of them is at the outskirts of the overdensity. So we can measure the overdensity for one of them, but we cannot measure it for the other. So as a conclusion, 1/3 of our submillimeter galaxies, they reside in dense environments, which is in agreement with previous studies. Also, they are compact groups when they are found about 200 kiloparsec of extension, which is also in agreement with previous studies and in agreement with the studies about the environments of quasars, which means that these quasars could be actually the population that, that quenches the star formation in the evolution. And we find no correlation between redshift and clustering strength. 7 of these sources are confirmed spectroscopically, and we didn't find any cross matches at low redshift. But as I mentioned again, this is a grain of salt because there are too many biases involved to study the environment of these sources at high redshift that we hope we can overcome with either with spectroscopic campaigns that are directly pointed towards the study of these sources, and also with new missions that are going to be launched very early, like the James Webb Telescope and Euclid. And for future work, we are trying to extend the method to be able to detect overdensities and megaparsec scales, and also to extend the method to avoid this problem of that the submillimeter galaxy is considered at the center of the overdensity. So we're trying to consider that the galaxy can be at any part of an overdensity. And this very same method can be applied to a different population of astrophysical sources. So thank you very much.
Thank you, Nuria. Thank you very much for your great talk. We have plenty of time for questions in case any of the participants, attendees want to ask something. There are even also people cheering. So let me see. Please raise your hand. I think there is a one hand already. Where is it? Oh yeah, Patricia. Please go ahead. Turn on your camera if you want.
Thank you, Nuria, for the nice talk. I enjoyed. Do you have any idea? I mean, you saw the comparison of the reside that you derive versus the one that the Cosmos team derived. So, do you have the masses of the galaxy? I mean, I'm wondering because you didn't specify what was the criteria for you to consider a galaxy as a submillimetre galaxy. I guess it's just detection. And so I'm wondering what type of galaxies are those? I mean, because now the sensitivity is much higher, no? And probably you don't have such monsters like the first submillimetre galaxies that you described in the introduction. So I would like to see, yeah, you have an idea of the mass distribution of your galaxies, and yeah, and that. So it was rest.
Yes, I mean, I don't know, but I can point you towards people who know, because they gave me like I'm an expert on the methods. So I mean, there is an extensive study of this sample. So I don't know, but I mean, there's a lot of work that has been done in this sample. So I can point you towards the masses of the sample. And there's been a study of the SMGs, there's been a study of the map of dust, there's been a study about everything, but I don't know. I mean, I haven't studied that.
Okay, thank you. No, that'd be great. Send me the reference.
Sure, I will.
Thank you.
Any other question for Nuria? Okay, since there are no people asking, I have a question myself. You mentioned at the end of your talk that, well, there may be some spectroscopic campaigns will help. I mean, given the size of the overdensity region, right, which is even a resist as well close as 3 is within half a minute. So I was thinking, I mean, if you point to these SMGs with Muse, you will cover the entire overdensity region. Even in the ones that you don't see the overdensity region, it probably is very high density at that size. And you can do a full spectroscopic survey of the entire field. And probably you can go deeper than the current spectroscopic catalog. And also especially because when you try to see the density environment of a bright source, because some of these probably are optically also bright, not all of them, of course, but some of them could be. But certainly probably are brighter than the companions around.
Yes.
So that sometimes when you do the spectroscopy, because you have your slit or your fiber on that source because it's bright, of course you want to have the resist too, but then you cannot put any other fiber around. So that might actually bias against having resists of galaxies very close to a more bright galaxy, to a brighter galaxy. So, but if you do a full spectroscopic survey with Muse, for example, you wouldn't unbias your spectroscopic resists because you will have everything in that field, even in the ones that are not considered based on your method to be in overdensities.
I know they're doing campaigns with ALMA, so not the spectroscopic in optical, because you're right. I mean, if you place the slits, I know about the spectroscopic in the optical, but not with ALMA. So you're right, if you place the slits, you cannot place them so close because you will have contamination from such a bright source. But a couple of them, they have been doing it with ALMA, and they obtained amazing results for a couple of these sources. And I don't know if they are, I mean, probably they are trying to point towards more ALMA rather than optical instruments.
Yeah, but I mean, as you said, probably in the very high resist, most of the companions are star forming too.
Yes.
Not all of them are going to be as dense as the SMGs. So you wouldn't, I mean, I understand that because you have your central galaxy SMG, ALMA sounds like great, but for the other galaxies around, which are probably, I don't know, blue nuggets, let's say, things that are not so dusty, might not be the most efficient way because you might not have such a high metallicity to have high dust content. And again, you will probably bias to the most massive of those systems. While if you go to Muse, you might get this low metallicity or comparative or low dust content companions, which again count on the environment overdensity estimates, right?
Right. You're right. And also with Euclid and with the James Webb Telescope, we're probably getting a better coverage and deeper. So our biases will be solved partly, but yes, I mean, you're giving a great idea of how this can
Sorry,
be.
I'm completely IFU biased.
Yeah, of course. we are all biased.
Exactly. So any other question for Nuria? No? Let me see, let me check the chat. The chat of the YouTube video. Okay. So if there are no more questions for Nuria, let me check again.
I'm stop sharing.
Okay. Okay, I don't see any other hands. So let's thank Nuria again. Thank you again, Nuria. And well, if any of you has any doubt, the presentation will be also, it's already available at the YouTube channel of IPARCOS. And so we'll see each other. Let me see what is the next seminar that we'll have is, just a second.
It's next Friday, September. Yeah, March.
Oh, you have it. Okay.
Yeah.
So we have Hugo Tabernero. No, Wednesday actually.
Okay, but in the webpage it is broken again.
Oh, okay. So maybe my mistake. Yeah. So next week we'll have Hugo Tabernero from the Porto University talking about a tale of two stellar characterization codes. And so we hopefully see most of you next week. And so thank you again, Nuria, for the talk, and thanks everyone for participating. Have a good day.
Bye.
Bye.
Bye. Bye, everyone.
Armando, puedes cortar el YouTube Live ya.
Sí.